Okay, good people. We are now doing 1.6. You probably had a feeling we are going to do this, especially after we had recently finished 1.5. Get it? Anyway, if let's look at the first theorem. If p is a prime number and m is any integer, then m either is divisible by p or is prime to p, meaning relatively prime to p. And meaning has no common factors. So either it's so in other words, if p is a prime number, any other number is either a multiple of the prime or it's relatively prime to the prime, meaning has no common factors. And this theorem follows from the fact that the only divisors of p are 1 and p. Now, let's go on to the next one. Number 2, the product of two integers, each less than a given prime number p, is not divisible by p. So if I have two numbers that are less, so p is a prime number, like 7, and 2 is less than 7, 3 is less than 7, 2 times 3 equals 6, so 6 is not divisible by 7. Or let's say I would take a bigger number, like 4 and 5. 4 times 5 is 20, and that is not divisible by 7. So if I have two numbers, each of which is less than my prime, and I multiply those two numbers together, the product the product is not divisible by said prime. Okay, so let's prove that. So we're going to let a be a number which is less than p. That's what we're talking about. And we're going to suppose that b is also a number less than p. And we're going to add the condition that ab is divisible by p. So this is what we're going to, so now this is what we call, like a proof by contradiction deal, because we're assuming something that the theorem says is impossible. But we're going to assume that AB is divisible by P. And we want B to be the least number for which AB is divisible. So we want B to be the smallest number that there is. There might be more than one number, but B should be the smallest one where AB is divisible by P. And A and B are each less than P. So then, evidently, there exists an integer m such that MB is less than P, which is less than n plus 1b. Meaning if I keep on taking multiples of b, if I keep on taking multiples of b, eventually I'm going to get to almost up to that prime number, and then the next multiple is going to be just over the prime number. This is a similar argument we saw before. Now, I'm going from this three-way equation. It's actually inequality. It's a what do you call it? Compound inequality. I'm going to subtract mb from each side. So when I subtract it from here, I get 0. Subtract it from here, I get p minus mb. When I subtract from here, I just get b. So I have here p minus mb is less than b. Now, since ab is divisible by p, it's clear that mab is divisible by p. And ap is also divisible by p. So the difference of AP minus MAB, which I can factor out to A, is A times P minus MB. That's going to be divisible by P. Well, that is what it was saying here, is that the product of A by an integer less than B is divisible by P, and that contradicts the assumption that B was the least integer. That's the story. That's how we contradicted it. So the assumption therefore is not true because it led to this contradiction, and thus the theorem is proved that the product of two integers, each less than a given prime number p, is not divisible by p. And how do we know? Oh, never mind. Okay, moving on. Number 3. If neither of two, is it neither or neither? I never knew the difference. Of two integers is divisible by a given prime number, P, their product is not divisible by P. So if I have two numbers, neither one of which is divisible by a prime P, like two numbers, neither one of which is divisible by 7, their product is also not going to be divisible by 7. That's really what this is saying. And let's see if we can prove it. So we're going to let A and B be the two integers, neither of which is divisible by the prime P. And according to the fundamental theorem of Euclid, that's what we just did previous section, there's this integers m, n, alpha, and beta. This is like that like division algorithm thing, that division thing. A is equal to mp plus alpha, B is equal to np plus beta. Alpha and beta are each less than p, so they're the remainders. And what I want to do is I want to take these two equations and multiply them together. One multiply the two left sides and multiply the two right sides. And usually we have two equations, we add them together. Here we're multiplying them together. So I'm multiplying because equals multiplied by equals are equal. So when I multiply the left sides, I just get AB. When I multiply the right sides, well, I get this whole mess over here, which I have to FOIL out. And I'm going to FOIL out, regroup everything, factor out a P, and we get a whole bunch of junk here, oops, times P, plus alpha beta. So AB is equal to a whole bunch of junk times P plus alpha beta. Now, if we suppose AB to be divisible by P, so we have alpha beta also divisible by P. And this contradicts number 2 because alpha and beta are less than P. So can't work. So hence AB is not divisible by P because alpha beta cannot be divisible by P. And that's it. We're done with theorem 3. And of course, theorem number 4 is just taking this same thing. I didn't even highlight it because it's just taking the same. I'm going to temporarily highlight it, but not save it. Theorem number 4 is really just taking this, just extending it to more numbers. If no one of several integers is divisible by a given prime P, their product is not divisible by P. That's all we're saying here. Alrighty. Well, that is that. It's been loads of fun. And our next video will take us into the world of 1.7. We learned a lot in 1.6 about divisibility of by prime numbers. And I will see you guys next time. Bye, everybody. Stop the recording.